everyone, welcome to my channel. In this video, we are going to be seeing about the 23rd module of the ISS, the JLM, Japanese Logistics Module. Let's start the video. The Japanese Logistics Module JLM, known as Kibo, is a vital component of the International Space Station ISS that serves as a multifunctional laboratory and storage facility. Developed by the Japan Aerospace Exploration Agency JAXA, Kibo supports a wide range of scientific research and international collaboration. Kibo, meaning hope in Japanese, is the first permanent research module of Japan in space. It is designed to provide a platform for scientific experiments in microgravity and to support Japan's contributions to international space research efforts. This laboratory consists of three segments: GEM, JEF, and JLM. The Japanese Logistics Module JLM is positioned on the zenith space-facing side common berthing mechanism of GEM experiment module. The JLM, part of Kibo module on the ISS, is sometimes referred to as the attic of Kibo. This nickname comes from its primary role as a storage area for experiments, tools, and other supplies used in the Japanese experiment module GEM. The JLM sits atop the pressurized module PM of Kibo, much like an attic in a house. Although smaller and not meant for crew habitation or conducting experiments, it plays a vital role in supporting Kibo's operations by providing easy access to storing equipment, scientific samples, tools, and experiments. The Japanese Logistics Module JLM was launched as part of the ISS Assembly Mission 1J or A, STS-123, along with the Dexter Canadian Robotic System. This mission also set a record for the longest shuttle stay on the ISS, lasting 15 days and 18 hours, and was the first to fully utilize the Station to Shuttle Power Transfer System SSPTS, allowing power from the station to support the shuttle systems. On February 18, 2008, the crew completed a terminal countdown demonstration test in late February. The actual launch occurred on March 11, 2008 at 2:28:14 EDT. During the launch, there were some minor technical anomalies, including a switch in the flash evaporator system controller and a failure in the instrumentation for some left side control thrusters. However, these issues were not expected to affect the overall success of the mission. The STS-123 mission not only marked a significant achievement for NASA, but also strengthened international partnership in space exploration, especially highlighting Japan's contribution to the ISS. Once in orbit, on flight day 1 of the STS-123 mission, the crew conducted a series of observation checks and preparations, which included performing orbiter maneuvering system OMS burns to ensure a stable orbit of the shuttle Endeavour. As the mission progressed into flight day 2, Endeavour closed in on the International Space Station ISS. The crew utilized a 15-meter laser-tipped boom to inspect the shuttle's wings, known as the Orbital Boom Sensor System (OBSS), following standard procedures established after 2003 Columbia disaster.
So it's a Friday 3 time for rendezvous with the space station. Now we are
on flight day 3, Commander Dominic Gori executed a 360-degree backflip known as a rendezvous pitch maneuver or RPM, allowing for the detailed photographic documentation of the shuttle's thermal tiles before docking.
is taking pictures of the shuttle tiles to make sure that we don't have any.
The docking took place at 3:49 UTC, and the hatches between Endeavour and the ISS opened at 5:35 UTC. Following the successful docking, the pallet carrying Dexter was transferred to the payload ORU accommodation POA of the Mobile Base System MBS using the Canadarm2 robotic arm. marking a significant step in the mission's objectives. On flight day 4 of the STS-123 mission, spacewalkers Richard Linhan and Gerard Reisman began their work on installing the special purpose Dextro's manipulator Dexter. However, they encountered an issue when the Space Lab pallet carrying the SPDM failed to power up. Ground engineers attempted to resolve the problem with a software patch, but later investigation suggested that the design flaw in Dexter's temporary power cable might have been the issue. Despite this setback, the crew aboard Endeavour continued their operations by using the robotic arm to remove the Japanese logistics module from the shuttle's cargo bay at 8:06 UTC. The JLM was successfully attached to its interim location on the Harmony module of the International Space Station ISS. Flight day 5 began with the crew outfitting the Japanese logistics module by transferring supplies and equipment from Endeavour. At 1:59 UTC, the station's arm operators grappled the Canadian-built Dexter, successfully powering it up 11 minutes later. Linhan and foremen conducted the second spacewalk, lasting 7 hours and 8 minutes, during which they completed the assembly of Dexter. They faced challenges removing the 2 transport bolts, eventually using a pry bar for assistance. March 24th, flight day 14, was the last full day for the crews together, with off-duty time followed by wrapping up equipment transfer and preparations for undocking activities. They held a joint news conference answering media questions. March 25 saw the hatches between Endeavour and the ISS close at 21:49 UTC, leading to a scheduled undocking at 23:57 UTC. Due to a command issue with the ISS solar arrays, undocking was delayed by 28 minutes, eventually occurring at 00:25 UTC on March 26. The shuttle landed at the shuttle landing facility at Kennedy Space Center at 00:39 UTC, completing a 16-day mission with no significant issues. Despite some initial concerns regarding the exhaust from shuttle's APUs, the mission concluded with wheel stopping at 2040 EDT, marking a successful return from a comprehensive pivotal mission. The Japanese logistics module is equipped with several key components to facilitate its operation on the International Space Station ISS. Now, let's see about each part in depth. The grapple fixture on the Japanese logistics module JLM is a crucial component designed for robotic operations. This fixture allows for the module to be captured and maneuvered by robotic arms such as Canadarm2 on the International Space Station ISS. The JLM features 4 trunnion pins that play a vital role in its attachment and positioning. These pins are designed to ensure a secure and stable connection for payloads or experiment to be attached. The CBM common berthing mechanism passive port on the JLM is integral for its attachment to other modules on the ISS. Currently located at the Zenith active port of Japanese experiment module, it serves as the only passive CBM available in the Japanese experiment module system. The JLM Japanese logistics module has a diameter of approximately 4.5 meter 15 feet and a length of 4.5 meter 15 feet. In conclusion, the Japanese logistics module JLM serves as a vital asset to the International Space Station ISS, facilitating a wide array of operations that enhance the station's capabilities. I hope this video on the JLM module was interesting and informative. I'll meet you in the next video with another interesting topic. Take care. Bye.